you beat him. It's always- So after today's lecture, we have two more lectures, like next week, there are two classes, and then we have the exam on Friday. Uh, about the homework and other things, I think I will have a more clarity on when it is due and when I will post the final exam. Probably early in the next week, I'll be able to post the take-home part of the final exam. Is that clear? So the final exam will have two pieces. There will be about 2 or 3 questions which will be in class, like I said, during the exam, and another 2 to 3 questions which will be take home. But the take home part will be before. You have to do it at home and then bring it to the exam instead of uh, taking it to your home during the exam. So I intend to post the take home part early in the next week. So you have probably more than a week to work on it. And surely by Friday, but hopefully earlier than that. Okay.
Do we have more homeworks?
There will be one more homework for sure. And that is what basically I'm deciding on the content, how much to cover. So it's not about making the homework. Uh, it, I was planning to do spherical harmonics also, but then I was debating today whether to cancel the class or not because I was a little sick and I decided not to cancel. And at that time, I realized that maybe I'm covering too much. So I'm confused a little about that, how much to cover. So the homework will change accordingly. So it's more about what questions to put in the homework rather than making the homework. Does that help? Yeah. Okay, Newington is not bad. So we surely have homework 12. The there will be a homework 13 also. This will be officially due December 8th. And that is because I cannot make a homework due after Friday. That's the last day. At least that is what I know. I mean, again, one might ask, is that officially? At least I remember in one of the university I was in, there was an official rule that you cannot have a homework due during exam week. I don't know about SIU whether that is a strict rule or not, but that's a good thing to have. So I'll make it due here, but then I'll be very lenient about it. You can take the time, but surely not after final exam. The final exam, I need everything because I need to finalize the grades. Is that clear? All right. So that's for 13, and then there is a final. So that's 3 things. Remaining what's number 15, Friday, And that's 8, 8, 10. This is on Bessel functions. This will be on legendary polynomials. This is on Bessel. And I was thinking, I'm still debating, maybe spherical harmonics can come in here, but probably not. Okay, yeah, let's see. Okay. And I will also help you with the homework today, so that might help you. Any other questions you think I could address here? Okay. Move this out a little. Okay, we talked about Bessel functions. Give the definition at least. If you're talking about the zeroth order, that is k0 of t, so it's basically a function. And it is primarily, you can think of it as an integral which cannot be done. But this is the zeroth order. And then there is the m. We started by defining the zeroth order. And that was defined as 0, 55. What is the parameter? Show that take alpha probably. 5. 5. Huh? Was it alpha or 5? Alpha. Doesn't matter, it's a dummy variable, but and then there is I, P cosine alpha. So that's zeroth order. And if you were to, if you want the nth order, there's minus I n alpha. You can also write it as a product of two exponential, doesn't matter. It's clear that when I set m equal to 0 here, I get that. So that's your definition of Bessel function. Whenever we have special functions, two things we try to find out is one is its differential equation. So usually functions satisfy a differential equation. I guess a lot of property, but it should be a completeness of, let's say, first is differential equation, second is completeness relation. And third is orthogonality, orthonormal. You should, if I were to give it importance, I think completeness comes first, that it's a vector space or a Hilbert space, and then comes orthogonality, which gives you the basis functions, and then comes the differential equation. But that's a matter of choice as to which one is more important. I wrote it this way because today here, let's derive the differential equation for this, and then we will do the modified Bessel function in the homework, and then do the Green's function also in that. So how does this go about? So let's to get the differential equation satisfied by this, there's a nice little trick you can use. And remember, historically, what happens is that Newton gave the idea of gravity. So you have 1 over r potential. So Newtonian physics, if you think of it, the force between two masses is equal to minus g m1 m2 over 1 minus r2. And there's the magnitude square. And what is missing here? The vector sign direction. And it says that this is inward, right? like R is outside, is radially outward 1 to 2, and this is attractive, so that's in the you also have the potential associated with it. So potential will be minus G M1 M2 over R1 minus R2. And of course, the force is equal to negative gradient of the potential energy. And this was very important. Notice the once Newton gave this, you could start predicting stuff. You knew how moon goes around the earth, you knew how earth goes around the sun, and in fact you could talk a lot about all the planets, and within no time, within about 100 years, you could actually talk about where the planet would be to great accuracy within hours, if not like these days we can tell it to within seconds. But in those days, even within hours, that was great. You could predict solar eclipses and so on. So there was a lot of work related to that. And Bessel functions was coming in the picture. So if you're working with this, if there is a function that is very crucial, then you want to understand that. So let's see how in this context, Bessel function comes in. And also remember that your electrostatics is very similar, right? So this is it's plus, right? So it's plus 1 over 4 pi epsilon naught. Q1 Q2 over R1 minus R2 times R hat. And the potential energy is equal to plus 1 over 4 pi epsilon naught times Q1 Q2 square, right? R1 R2. And again, you have force is equal to negative gradient of potential energy. This is electrostatics. This is gravity. Electrostatics has a nice feature that divergence of the electric field is equal to the charge density, so that equation is valid. Here, historically speaking, most of the work related to Bessel function was done in the context of gravity. And it was used in electrostatics a lot, but they are both mathematically identical. What is the equation satisfied by this equation? And we learned that it is del square. So remember, we are interested in the differential equation for Bessel function, and I'll motivate how this Bessel function goes up here. Del square times electric potential, let me call it phi. Right? So del square of phi, or let me make it better, right? We will do this in electrostatic context. In electrostatics, we have this equation, but not plus. So you have divergence of epsilon naught times the electric field is equal to charge density. This is charge per unit volume. Most of you doing electromagnetism in a parallel course, and electric field is equal or defined as negative gradient of the electric potential, not the potential energy. It is the electric potential, and immediately you get this equation that del square of, let's say, epsilon naught times phi is equal to charge density. If you have the charge density, usually the goal is to find the electric potential associated with it. We are interested in a Green's function. You can immediately say that the Green's function associated with this would be del square times G of, so this is R. So this is R, R prime. Will be 3 delta functions. So that's how you define your Green's function. We have defined our Green's function. The interpretation is immediate. If you have a charge density, this is the electric potential. Give me a distribution of charges. There is an electric potential associated with that. If you have this as your charge density, and this means a point charge. right? There is only one charge and it is there at one point, and that's the Green's function is the electric potential associated with a point charge. And what is the electric potential due to a point charge? So it is Q1 Q2 over R1 minus R2, and since epsilon naught, I'm not having Q, I'm not having, so G will be equal to, so G of R comma R prime is equal to, there is no epsilon naught because I pulled it out here. So there is 1 over 4 pi. There is no charge here because charge is the dimensions of this is charge, so there is only 1 here. So there is no Q in there. So it is simply R minus R prime. Like that's the same equation that Q1 and Q2 is not there and there is no epsilon naught. So it is at this stage, we don't care whether it is gravity or electrostatics. That's just a differential solution to our differential equation. So we know then that it should be true that divergence square of this function must be true. Right? This, if I were to evaluate this will come out to be a delta function. And we did this in a different context in the early part of the semester. If I were to evaluate this, you take the derivative explicitly. If I take the first derivative, it will give you the 1 over R square, and then I have to hit the R and R prime also. And if you explicitly do this, that does come out to be 0. And then you have to use the divergence theorem to motivate the fact that it's actually a delta function. Right? So that's a very sensitive argument that you have to go through. So it's a the electric potential due to a point charge comes into picture, or a point mass. Gravitational potential due to a point mass is into picture. Let's look at this more carefully. So we have the equation del square and G if I have that equation to be true, I can take a Fourier transform of that. Notice the fact that the Green's function is actually a function of R minus R prime. It doesn't show up in any other form, right? So only this particular Green's function is a function of R minus R prime. So if I'm Fourier transforming, well, let's say this is also R minus R prime. So a Fourier transform of that, remember Fourier transform, f of x. If I have f of x, a Fourier transform will be dk over 2 pi e raised to ikx, and then a function of k. That's a expansion in sine and cosines if you want, but you can think of it as exponential. In general, this function is different. This could be f tilde. Right? It's a different function altogether, but it is convenient to drop that tilde, and context tells you that if it's a k dependence and an x dependence, those are different functions. So these are different functions, but I'm not going to bother to write the tilde in that just to avoid some purpose. So that's Fourier transform. There is an x minus x prime here, y minus y prime in there, and a z minus z prime. And maybe I could also say what is the inverse transform? F of k would be equal to minus infinity to plus infinity dx e raised to minus ikx and f of x. This is a notation. Different people use different notation. We have to put this 2 pi. You can put the 2 pi there. You can put the 2 pi here, or you can distribute the 2 pi equally. That's a matter of notation. Certain things are good to make observation of. If f of x was equal to 1, so if f of x was equal to 1, that means it is a constant. Yes,
It means can we use 2 pi in both the equations?
Yes. So for example, and that is very common in quantum mechanics. So if you're doing quantum mechanics, you will do the following: dk over square root of 2 pi minus infinity to plus infinity e raised to I k x f of k, right? And then f of k would be equal to minus infinity to plus infinity dx over square root of 2. This is more symmetric in a sense. That efficient you have. In quantum mechanics, there are reasons to do this. I mean, everyone almost in quantum mechanics, they will do this. But when you're in general doing, there is a lot of freedom. You can have 2 pi here, not have a 2 pi there, or some people will put it here, not have it there. I at least try to be consistent with this notation. And yeah, so here in this course, we will use it for default. So we are not using this. It's good to have some extreme examples there. If f of x is equal to 1, right, that means it is a constant plot. So that we are asking the question, what's the Fourier transform of a constant function, right? X goes from minus infinity to plus infinity. It is just 1. If I were to plot this, it will be just like that, right? It's a constant. Goes all the way x to x. And then you ask, what is the Fourier transform of a constant function? Anyone immediately knows? If f of x is 1, what is f of k? Think of quantum mechanics again. If you have spread out in position, what happens to momentum? Delta function, right? Like Heisenberg uncertainty relation tells that if position and momentum measurement has to be having a constant, so one is infinity, the other one must be 0. So f of k here, and because of the 2 pi factors in here, so this comes 2 pi times delta function, delta k. So here, so this is like the k. So notice this has a spread 0, this has spread infinity. So this is a standard thing that comes in Fourier transform that way. But that's all information about Fourier transform. This is in 1 dimension. We are interested in 3 dimensions. So G of R minus R prime. What is the Fourier transform of this quantity? This will be having 3 integrals. Instead of having 1 integral, I have 3 integrals. The cube k. So there is a k in the x direction, there is a k in the y direction, and then there is a k in the z direction. Right? So this is k is equal to kx in the I hat direction plus ky, and the j hat direction plus kz in the k hat direction. That k is confusing, but this is the direction k, not the level. Okay. So that's dq over 2 pi whole cube. That's your integral, and we have e raised to I. Now there is x, kx times x, ky times y. That can be written as a dot product. K dotted with r minus r prime. It should be just r, but since this function is r minus r prime, I can write that as a as a as r minus r prime, and the Fourier transform of this, which will be dependent on k. So the question we are asking is the electric potential due to a point charge, which is 1 over r. Right? What is the Fourier transform of that? Like, what if we were to work in the Fourier space? What is the Fourier transform of an electric potential due to a point charge, which is 1 over r? We know the expression. What is the Fourier transform of that? That's a very valid reason to ask, or a valid question to ask. And so let's try to evaluate that. And notice you have this equation. Let's evaluate the gradient square on it. So gradient square of G is equal to Where is this gradient hitting? This is the derivative with x, derivative with y, and derivative with z. That's going to hit this R. That's the only place where it hits. There is no x dependence here. Nowhere else there is x dependence. It only hits on this. Exponentials are very easy functions, very nice functions. I know the derivative of exponential. So when the derivative hits on this, every derivative brings in an ik down. So gradient of this will be ik. So this will be equal to d cube k over 2 pi, the whole cube. Each derivative brings in an ik down. There is a negative sign. Two i's coming from the negative sign. So this is k squared. So I have k squared times exponential ik divided with r minus r prime and g of k. That's my Laplacian of the Green's function. What about the delta function? Because there's a negative sign. Right? Is that clear? So gradient of exponential of ik started with r. That went away outside. That's equal to I times k. Right? So two derivatives, del square is equal to ik dot times ik dot. That's equal to minus k squared. But negative of a gradient square will kill that. So good point, good question. But, so that's what it is. Do the same thing for delta function. Delta function, we set what is the Fourier transform of a delta function, right? Fourier transform of a delta function is 1. So if I want to write this as exponentials, this will be equal d cube k e raised to ik dotted with r minus r prime. And what comes here?
What is d squared?
D squared. Here, this one? No. I think. Huh? This one?
Yes, d squared.
S squared. I'm not understanding.
D squared can.
Oh, because of some mistake. I think I was having this in my head. This is the Thank you. Thank you. Thank you. Thank you. Yeah. Oh, again, I wrote the same mistake. So it was not that. I think something else. Because something else is going to come in Bessel function that's correct. So okay. I'm thinking ahead. Okay. Thank you. Yeah. So this is dq, of course. The three x, y, z, right? So each function we are doing. And what is coming here? What is the Fourier transform of? So Fourier transform of this is this, right? Or this is equal to this. So what is the Fourier transform of a delta function? It is 1, right? So that's 1. Right? So that is 1. Okay, that's what we motivated here. 1 is delta function. What that means is that this is equal. Right? My point charge is the Green's function is the electric potential due to a point charge. That means these two are equal, right? That's equal. Right hand side should also be equal. This is a complete set of functions. Fourier functions are complete set. That means the coefficients must be the same. So this implies, notice the language, this summation should be thought of as a vector. Like if a vector is equal, if two vectors are equal, its components are equal. So these are the components of this function. So these are components having 1. So this means that k squared times g of k must be equal to 1. Right? Because these are the components, like these are the basis functions. These are the components that must be true. Is that clear? Like think of a vector. If A is equal to 0, if A is equal to B, then you say the components AI is equal to BI, right? The three components of a vector, each one of them must be the same. So similarly, this is a Hilbert space, this has infinite dimension. So each component must be the same. This must be true. So we know the Fourier transform of our electric potential. Right? So this is the Fourier transform of the electric potential. It doesn't depend on the vector nature at all. It is actually dependent only on magnitude. This is 1 over k squared. That's the Fourier transform of your Coulomb potential, 1 over r that we write all the time. If you were to, for any reason, work in the Fourier space, that will be your electric potential. Okay, that's good. So I can now write this in this form here. But we are talking about Bessel function, right? Somehow I want to motivate the Bessel function. This is all very convenient when you're working in rectangular coordinates. So what I have motivated to you until now is, let me go back here. So I have 1 over 4 pi. That's my Green's function. That's your Green's function if you want. You are prime. That's equal. Oh, okay, we keep working. So that's your Green's function. And what we have shown now is that the Fourier transform of this, right? Fourier transform of this is g of k is 1 over k squared. So I can say that k dotted with r minus r prime is 1 over k squared. This is a true statement. If you want, this is an equality, but this is a Fourier transform of each other. Fourier transform of 1 over r is 1 over k squared. That's what it means. But let's process this further. Let me say that I'm not, so remember again, all this was in rectangular coordinates, and Bessel functions are more relevant in cylindrical coordinates. Like, let us say we are in cylindrical coordinates. Let me rewrite this equation a little. So I have x and y separated out. So dqk over 2 pi whole square, like a minus infinity to plus infinity in there. Okay, so and now I'm basically splitting, right? So this is d t k z. Okay, k part 2 pi. So what I'm doing is the k is that is a kx in the I hat direction, ky in the j hat direction, plus kz in the, let's say, z hat direction. This I'm calling this k part plus kz in the z hat direction. So the rectangular coordinates x and y is special, right? So that's x and y. That's a z direction. Okay. So think of cylinder again. Cylinder has x and y. You want to take it into the polar coordinates, and z stays as it is. So I'm going to take out the z part in here. So let's say that's minus infinity to plus infinity, and this is equal to e raised to I. So this also, there are two pieces now, right? So that is a k per dotted with r minus r prime per, this is x minus x prime and y minus y prime. And that is a new piece now, exponential ikz z minus z prime of k square is k perp square plus kz square. Just rewrite. Oh, camera is not set up properly. With me? Right, so we started with the Fourier transform of the Green's constant, and then we are saying that, oh, this is k perp square and k z squared, and this can come out, right? This is all k perp dependent. So let me separate this out. Q k perp over 2 pi whole square e raised to I k perp. Like I want to process z dependence, the kz dependence separately. Z over 2 pi and e raised to I k z over k perp square plus kz square. What is that integral equal to? Anyone recalls? This one, this integral, the z into kz integral. I think somewhere you did this as a homework. Somewhere means in my course. Hello?
In the analytic part.
Yes, in the analytic one, in the contour integral. Yes, very good. By any chance, do you remember?
2 pi times, no, not 2 pi.
Good. I think that's, so you're thinking, so this is integral, let's say dz. Let's write that as k, right? Kz 2 pi e raised to I kz kz square plus k perp, well, minus infinity plus infinity, right? So if you think of this, this is a real variable, take it to the complex variable. Right? So this is complex z, and then so this is k complex kz, and then this will have poles, right? So there will be an I k perp, and there will be a minus I k perp, right? That's your two poles, and then you again have to do this. This is what your integral is. You can either go up or down depending on where the z minus z prime is greater or less, right? And if you do that, it's only the poles that contribute. You can see that when kz is equal to I k perp, this will give you as a 2 pi, that is an I, that is kz or k perp times. If z is greater than z prime, it is plus, you go up or down. And whenever it is not, it's just k perp. So that's your integral. Using contour integral. I just argued it out. So if this is the contour you take with z is greater than z prime, and you take this contour with z is less than z prime. Okay. Maybe quiz, right? You have not had quiz for some time. Yeah. Right. So go back to your homework and just motivate it using that as to what that is. Right? So that's your integral. So that means that this is equal to d2k perp over 2 pi whole square e raised to I k perp. And integral is done. So that's k perp z minus z prime divided by 2 k perp. That's true. I mean, either I can write it this way or this way, both are true. Let's think of cylindrical coordinates. This is not. Then I will need that. And let's have, this is your case k vector here. Okay, perfect. And there is an r minus r prime. Let me say that's p, just for a shorthand notation. So p is basically r minus r prime. So if I'm doing k dotted with p, that's equal to k times p. If k is having alpha, so this is, let us say, having phi, so this is having phi, this is having alpha, so this is alpha minus phi. So I have k times p times the sine of phi minus alpha, alpha minus phi, or phi minus alpha. If I choose p in the z direction or p in the x direction, then phi is 0 and I just have alpha. So what I have then is that 1 over 4 pi, or let me write this as Green's constant. So Green's constant, r minus r prime, which can be in any coordinates. In cylindrical coordinates, this has this convenient feature that I can write this as magnitude paper 5. And let's say now k is with alpha, right? So this is d alpha over 2 pi, 0 to 2 pi. That is, now I'm going in the polar coordinates for k. K, the polar coordinates for k. And this is e raised to I k for p cosine alpha. I chose phi to be 0. And I have e raised to minus k half v minus v prime over 2k half. So this is where you get your Bessel function. I was trying to say that where is Bessel function coming in, that's your Bessel function. So you would say that the Green's function, k half cancels out, is nothing but, and so there is a 2 pi, so you have 1 over 4 pi times 0 to infinity, e k half times j0 of k half p. P is nothing but r minus r prime, or minus r prime, times exponential so that's the expansion of your Fourier, of your Green's function in terms of your exponentials, if you want. So that's, I was trying to say that back in the time when you were working with gravity, this came very natural because this was the potential due to its mass, right? If you have sun or earth, if you want the gravitational force, then or gravitational potential, that is what you will encounter. And that integral is not easily doable, so you would set that that's Bessel function and you form properties. So we are interested in the differential equation for this. And what we are encountering here is that the cylindrical coordinates has 3 variables, right? So there is a rho, there is z, and there is phi. Maybe I can write this the other way, right?
What's the argument for J now?
Argument. Okay. Oh, that's what was the configuration side. Yeah, so I forgot that one. Yeah. Okay. So this, right, the argument is this. Right, so IT, right? T comes here. Right, that's here. Rest everything is an integral. Okay, so usually what you do is that you start with the Green's function and write it in different coordinates. This is what you will do if you're working in rectangular coordinates. This is what you would do if you're working in cylindrical coordinates. Next week, we will come and do the same thing in spherical coordinates. Like that, the only difference is it is theta phi, right? So it is polar radius, angle, and z. Whenever it's rho, so notice this is your rho, right? That's the magnitude of your vector. That's a function, J0. Phi is an angle and it is exponential e raised to I m phi. And z is e raised to I k z. These are Fourier pieces. And in the radial direction, it's always a Bessel that comes in. In spherical coordinates, we will see that it is coming as it will be the spherical Bessel function that will come in. And let me now say that there is some j in here. Let me not just say that it is j0. So there is some j piece in there, and let us try to get the differential equation for this. So the goal is to get the differential equation here, or at least motivate the differential equation. So we know that Laplacian of the Green's function is equal to delta function here. So this is delta function. But that's equal to 0 if r is not equal to r prime. So r equal to r prime, almost everywhere r is not equal to r prime. There is only one point. So let me say that I'm in the region where r is not equal to r prime. So that's equal to 0. And then you realize that, oh, whatever is happening is in the exponentials. And let us try to say that this is del square. Whatever is remaining out of e raised to I m and z, that is the differential equation for the Bessel function, right? So this is going to be equal to j m. I don't know what it will be, so let's just say that it's j m. And which will depend only on the rho. This is e raised to I k z. And there is exponential of I and phi. This is equal to 0 if r is not equal to r prime. Which means that what is the Laplacian in the cylindrical coordinates? That's 1 over rho d by d rho plus rho times d by d rho plus 1 over rho square times phi square and plus d by d square. You must have seen this at various places by now. And that whole thing acting on your j exponential, jm, let's say, ikz e raised to I m phi is equal to 0. I'm primarily getting all these exponentials so that I know the action of this. And apply this whenever it acts on z, there is an ik that comes in, phi, there's an im that comes in, and we immediately get the differential equation. Various ways to motivate this, but I think this is nice. So there's a minus m square over rho square, and dz square is minus k square. And now exponentials can leave, so that's gm of this will be rho, this will be q. You will have to do a very similar thing in your homework for the modified Bessel function. So that's what you will do. So let me now at this stage, I'll give you some hints for your homework. Like we have about 15 minutes, right? So I think I can do the orthogonality also here, but I think since we have gone a little quickly, it might help to at least give you a feel for what the homework is asking for. Any questions at this stage? In a very similar way, you can do orthogonality also, but I'm going to skip that in lieu of giving you hints on the homework. Okay. So, in your homework, the question is asking. So you don't work with Bessel functions. Instead, you have modified Bessel functions. And the modified Bessel functions are we can have km of t. And remember, this is also can be written as cosine, right? So this can be, let me not tell you, but I must not confuse. So this is your Bessel function. So this is a modified Bessel function that's equal to let me check. So kmt is equal to 0 to infinity d theta. It's the same as d alpha, but now since we are in the hyperbolic regime, it can go to infinity. Remember, your sine and cosine angles are not, the hyperbolic angles are not 0 to 2 pi, right? The moment you go to imaginary space, then it can go to 0 to infinity. This is equal to cosine hyperbolic of m theta and exponential of minus t cosine hyperbolic. What is very similar, instead of exponential, you have cosine hyperbolic. Remember, exponentials can be written as cosine and sine, but all the cosines become cosine hyperbolic. That's the difference that is happening. And of course, your angle is no more going from 0 to 2 pi. For our purposes, this is a variable. Remember, we never try to evaluate this integral. Whenever you work on it, you will operate this differential operator on this t. The key is not to evaluate the integral. You only change the order of integral, don't evaluate them. We are only interested in the properties of the integral, not the integral itself. Okay. And Im of t is equal to d5 over 5 times 0, 5, and this is the sign 1, 5 is to 2 times the sign of 5. The main point you want is that if I were to plot this as a function of time, the I functions grow. So I of I0 grows like this. So this is I0 of t, I1 of t short from 1. So this is I1, I2, and so on. And they all grow up. And remember, t is only from 0. It doesn't go beyond that. So t is let's say infinity and greater than or equal to 0, because we will be talking in terms of radial coordinate. What about k? K will be infinity on this side, and it will go down. So that's km of t. All km's will be infinity at t equal to 0, and and 0 at infinity. This should be compared with your exponential functions. Like this property will be relevant in your boundary condition. So we have z. And if I'm talking in terms of exponentials, that's your exponential of plus kz. Let me just say, forget the k. It's plus z. And that's exponential minus z. Right? Once you have a differential equation satisfying something in terms of exponential, you write your solution as, so let's say you have a differential equation, let's say Green's function, right? So it's Green's function g, we wrote as a times exponential of plus z, let's say plus kz, and b times exponential of minus kz. This is how you work with if z was greater than, I think you write it the other way, right? So if z was less than z prime, and you say c times exponential of plus kz plus b times exponential of minus kz with z prime was less than z. If your Green's function has to be finite at infinity, at z if it has to be finite, this is infinite. Right? The only way it can be finite is c equal to 0. So if I tell you that the Green's function is 0 at infinity, c must be 0. So there are boundary conditions you can pick from here. Now the same idea you want to do with this. Now if you have Green's function here, you start by saying a times I m, and now it is rho in or t if you want. So this is rho plus b times km rho. If rho was less than rho prime, and you have c times im of rho plus b times km of rho if rho prime was less than rho. Now if g of 0, that means rho is equal to 0, is not, is finite. Usually Green's function is physical. It has to be finite at rho equal to 0. That means rho is less than rho prime. This means that km cannot come in because km is infinity at rho equal to 0. So this implies then b must be equal to 0. If t at rho tends to infinity is finite, which means it is not infinity, then you cannot have I in it. Then A has to be equal to 0. Is that clear, the argument? Because it grows. Right? If it grows, that is infinity, so I cannot have that piece at all in there. So this is the key pieces that you will need in your homework. So otherwise, it is very similar to your exponential. Here also you use these arguments, but now instead of exponential, you have this Bessel functions and keep it. Exactly like exponential, keep them. They don't add and subtract. Remember that you have this nice feature that plus kz e raised to minus kz is equal to 1. Right? Exponentials, that is a very simple relation. But you don't have this for Bessel functions like k m rho times I m rho. That's not simple. That is, it is not equal to one. Like you don't have this luxury or elegance that comes in Bessel function. That's the price you pay. So, but what you do is that whenever you have to write this in this form. That's it. There is no simplification. There is a simplification in exponential. In Bessel function, you don't have that simplification. So they will look a bit of clutter in your expression. That's everything is the same argument as far as I can see. Try to go over them. And again, if you go to my earlier semesters, we have worked on this. I have given lectures on this. You should be able to see all the steps in there. So hopefully this helps. Yeah, I gave you very broad strokes on it, but hopefully it will. I think I'm insisting that it should be done because it's the cylinder vessel, sorry, cylindrical green function, which is not usually available everywhere right away. So it should be useful somewhere for you. Okay, that is all. Finish early. Change. Okay. And hopefully you are not don't get sick from it. That would be really bad. Oh, that thing. One line. Yeah, just we'll look into it at the end. Okay. I think I can stop this.